Okay. Today's class we will continue with ellipsoid. So I uh, on Wednesday I discussed ellipsoid method. I want to sort of complete a bit of discussion on the ellipsoid method and tell you some implications of the ellipsoid method. There are some important. There's an important property. Essentially, it helps you identify certain problems which can be solved efficiently. So I want to discuss that. We'll spend maybe the first 1 hour studying that. And then the second hour, I'll just introduce to you interior point methods. And just a heads up, from next week, we will start doing discrete optimization. I'll be spending 3 weeks after that just doing discrete optimization ideas. Okay. Okay. So let's remember where we were last time. So last time I tried to introduce the ellipsoid method. Okay. So just remind you what the method is. Okay. So we were looking at a feasibility problem. Okay. So you have a polyhedron given to you, which might be empty or non-empty. Okay, so you've got a polyhedron of this type in dimension in n variables with m constraints. Okay, so there are m inequality constraints, let's say, and n variables. Okay, and you have got the following question. It's a feasibility problem. So you have to so the algorithm has to do one of two things. One, either say that P is empty. So it has to either say is P empty. Okay, and if P is non-empty, it has to be able to identify that along with a certificate, basically a point x star which lies in the set P. Okay. So given any polyhedron, you want to do one of these two things. So you either want to find that the set is empty. If it is non-empty, you want to find a point in the set. Okay. So that's the what's called the feasibility problem. And it's a linear feasibility problem because there are only linear constraints in this problem. Okay. Okay. And the way the ellipsoid method solves this problem is so we know how to do this. For example, we have seen simplex, for example, like we can use simplex to do this. Phase one of the simplex will basically do this essentially for us. Okay. So we could have done simplex with this and solve the problem, but ellipsoid tackles this problem in a completely different way. Okay. It basically says that you start with so you don't know where the polyhedron lies in the set, but somehow you try to find an ellipsoid which contains this polyhedron. You're guaranteed that if the polyhedron is not empty, you're guaranteed that the ellipsoid will contain this. Okay, so you have to find a large enough ellipsoid which is guaranteed to contain the polyhedron. And of course, this will depend, how you find this ellipsoid will depend on A and B. And you basically look at, so this is your starting ellipsoid. And every ellipsoid comes with two things. There is a center point, let's call that x0, and then there's a scaling matrix basically which tells you how the ellipsoid looks like. Okay, so is it long in this direction or along the 45 and so on. So there is some sort of diagonal. There's a matrix which is a positive semi-definite matrix which you can basically initialize the algorithm with. Okay, you take the point in the center and you check if it lies in the set P. Okay, so in this example, x naught does not lie in the set P. So what the ellipsoid method does is it tries to find what's called a separating hyperplane. So it finds a hyperplane. So it finds some sort of cut. So this is a linear inequality. Okay. Let's say it's greater than or equal to x naught. What we are guaranteed is that the polyhedron lies on one side of this hyperplane because the P lies on one side of the set. So what the ellipsoid method does next is it tries to find a second ellipsoid which contains the intersection of this hyperplane, or this rather the intersection of this half space along with E naught. So you look at the set, intersection of this set with the ellipsoid, that's basically this body. Okay, this is not an ellipsoid, it's a half ellipsoid basically. So you have to find an ellipsoid, a nice circular body which can encirculate this. And you can do this, there's a formula which does this. So maybe it looks something like this. Okay, that's an ellipsoid, and maybe you get a point, let's call this x1. Okay, you check if x1 lies in the set P. How do you check it? Of course, one way is to check if it satisfies all these constraints. Okay, if x1 does not lie in the set, you find a second constraint. Maybe the inequality, you find a inequality which goes, let's say, in the side. This is A transpose X greater than or equal to X1, A transpose X1. So to find this A, okay, so this A will be different. If this is A0, A0, this is A1, A1, you find A0 and A1 and so on. Okay, so you find this hyperplane which cuts Rn into two parts so that the polyhedron lies on one side of this set, basically. Okay, now again, you find, so you're now looking at the intersection of this set with this new polyhedron. So if the original polyhedron was E naught, the new, if the new original ellipsoid was E naught, this new ellipsoid is, let's say, E1, center X1 with a matrix D1. And then you now find a new ellipsoid which contains the intersection of E1 along with this hyperplane. Okay, so that will give you a new ellipsoid. Okay, so you have this. So you have this ellipsoid. So you find me a new ellipsoid, basically. Okay. Um, okay, and so you will create a new ellipsoid. Maybe it looks something like this. Sorry, it should contain the. Okay, and you repeat, and maybe the center now lies somewhere here, x2, and you're done. That's the method. Okay, is the method clear? The ellipsoid method. Okay, so we discussed this last time, and I basically told you the. Uh, I gave you the formula. Okay, so the key step of this is the following. Essentially, it tells you that at any step, so if you start with an ellipsoid, let's say at a point uh, x and d, I think I give you a formula. Let's say the center is x and d. You move to a new ellipsoid, E bar, with a new center x bar and d bar. Essentially, there's a formula for finding x bar and d bar in terms of the original parameters and the a and the b. Okay, and so this is the old ellipsoid. This is a new ellipsoid. The key property that this ellipsoid satisfies is that the volume of the new ellipsoid, E of x bar d bar, is below, it satisfies this condition, volume of the ellipsoid of x comma t. Okay, this one I did not prove. Okay, so you have to use basically the formula of the volume of an ellipsoid, and you have to use the formula that I gave you for generating x bar and d bar. Okay, so this one is there in the notes, but for now, for us it's enough if you just we just take what the implication of this formula is. Okay, it can be proved formally. Okay, the textbook has it completely. In the notes, I've given it to you for a special case. Okay, okay. So what is the implication of this? The implication is at every step, this number, essentially, this number is something which is positive clearly, and it's clearly positive, uh, and it is less than 1, right? Because this is e to the power some negative number. Okay, so basically what's happening, at every time the volume of the ellipsoid is shrinking. The new ellipsoid, you now take the old ellipsoid and you take this ellipsoid, and the new ellipsoid will again have a factor. So after k iterations, what happens? So after k iterations, so let's say I run this ellipsoid k times, the volume of the ellipsoid at step k, okay, let's call that ek, the kth ellipsoid, will be e to the power minus this exponential term is multiplied k times. Okay, and because of the property of the exponential, this is e to the power minus k by 2 into n plus 1, the volume of the original ellipsoid that you started off with in your problem. Okay, this is just an implication of this condition. So if you believe this condition, this is a natural uh, implication of this, right? I just do it k times iteratively, so I'll get e to the power minus k by 2n plus 1. Okay. Now, if my p is non-empty, okay, when I do this k times, at some point this number, this ellipsoid will become lesser than the volume of P. Okay. So how long will that take? So I have to keep decreasing this till this becomes lesser than the volume of P. Okay. So that will, how many iterations will that take? So it will be volume of P. If you solve for this, basically e to the power minus k by 2n plus 1. I mean, how long will it take for this volume to be basically lesser than this number, basically? Volume of E naught, okay? If you take this to the other side and you take a log transformation on both sides, you can check that after so you will find the xk, the kth center in P after how many? You need to make this basically this thing equal. So at what point will this happen? Basically, you can check. It will be log of, so it will be 2 times n plus 1 log of the volume of the ellipsoid E naught by the volume of P. Okay. And these things might be fractional numbers and so on. So definitely after, if you round it up after so many iterations, you will find the solution. Is that clear? I'm basically checking at what point does this ellipsoid become smaller than the volume. At what point is this number, volume of ek, lesser than volume of P, basically? At what point? So at what k will this number become smaller, basically? Okay, and you can check that clearly at k with so many iterations, you will be done. Is that clear? You just make this equal, move this side, take log on both sides. You'll get a factor of 2n plus 1 log of the volume of E naught by volume of P. Okay, that should be clear. Okay, okay. So you have an algorithm. It tells you how many iterations. Okay, this is linear in n. Okay, so that's nice. Okay, the number of iterations doesn't grow. Okay, I mean it doesn't grow exponentially in n. Okay, what matters to you is the volume of E naught and volume of P. Okay, so you need to have some formula for this. Okay, so again, we will not do the full formula for this, but let me just give you a sense that these numbers will actually grow only polynomially in the input. Okay, so for example, um, so let's take an example of what these numbers might look like. So as an example, to give you some intuition, suppose my polyhedron is a box. Okay, let's say polyhedron is a box between 0 and a to the power n. Okay, so it's basically a hypercube. Okay, so 0 to, let's say, a1 and 0 to a2 and so on and so forth. So when I write it like, actually, let's make it all the a's the same, even for simplicity. So basically, this is a hypercube of along each dimension, I'm of size a from 0 to a, and I have this n times basically. Okay. So in 3 dimensions, this would look like a cube basically. Okay. And in n dimensions, it's called a hypercube. Okay. Okay. So what is the volume of this? Okay. So I want to find the log of the volume of P, right? So what is the volume of P? A to the power n. Okay. What is the log of the volume of P then? Natural log of volume of P is what? It's n log A. Linear dependence in n, logarithmic dependence in A. Okay. Remember how you write the polyhedron. This polyhedron can be represented as simply xi between 0 and a for all I going from 1 up to n. Last time when I discussed the representation of the input, I want things to grow polynomially in if my number of variables is n and number of constraints is m, I want it to grow as n and m. And in my input parameters of the matrices A, B, and C, I want it to grow logarithmically in the bit representation. So I'm getting log dependence on A, which is great. This is exactly what I want because this is a polynomial input this is a polynomial input size. If I'm going to store a number A, I don't require A bits. I need log A bits, basically. Okay. So this is exactly, so this type of So the volume of the polyhedron is actually logarithmic in the so this is actually polynomial in the input size. Great. The volume of E naught. So it depends on how you find E naught. But a simple ellipsoid in this problem is the following. You simply, so what ellipsoid will contain this box? An ellipsoid with the center at a by 2 and a large enough radius. Okay. So, so here's an ellipsoid which will contain the box, this box. Take the ellipsoid x in Rn, where I let my center be a by 2. I square this, and so this is less than equal to 1. So I need to get the denominator right. So for example, when xi is, let's say, a, this will give me a by 2 squared. That's a squared by 4, basically. Okay. And I'm added up n times, basically. So I get n a squared by 4. Okay. So I'll have to scale this down. So this should be n a squared by 4, basically. So you can check that any x, it's easy to check. If x lies in the polyhedron, it implies x lies in the ellipsoid. Okay. This is a large enough ellipsoid which contains a polyhedron. Okay. So this is going to be a large enough ellipsoid. Okay. Of course, in 3D, it's like a, I mean, it look like a conical shape with curvature. Okay. The center is a by 2. Huh? Is that clear? So do you believe that if you put all the x's to be zeros, you will get n a squared by 4, n a squared by 4, that's equal to 1. That's the boundary of the point. Okay. So actually, this will touch the boundary points. Okay. Okay. So what is the volume of this ellipsoid? So it turns out the volume of an ellipsoid of this type is directly proportional to the to this number, basically. Okay. So if you, it's essentially, you have to take, if you look at an ellipsoid, so it's basically, you take this number, it's a square root n by 2, that's one term, you multiply it n times, basically. So you multiply it with itself n times. Okay. So that's basically, I mean, you can look at the volume of an ellipsoid is directly proportional to this number. Okay. Basically, you take, I mean, okay, maybe if you want, so if I give you a ellipsoid of this type, summation I equal to 1 to n, in fact, this is actually this is not even a, this is even, this is actually not only an ellipsoid, it's actually I mean, it's essentially like a ball centered at a point. Okay. So, so if I take a ellipsoid of this type, essentially the volume of this ellipsoid is proportional to this, all these numbers, di. Okay. This is a formula for an ellipsoid. You can check it up. Okay. Okay. So what is, so again, formula is not critical for me, but let's look at what the dependence is. The log of this volume. How does this change with n? It's directly proportional. So this will be basically order of n log a plus, I mean, I'm not, I don't, not particularly bothered about the constants, but basically n log a, that's like n log n, basically, roughly, right? N log of n square root of n, that's basically n by 2 log n. So basically, the dependence is n log a plus roughly n log n. Okay. This is again depending linearly on n, actually not linearly, linear plus logarithmically, but there's polynomial dependence in n, so at most quadratic in n, and logarithmic in a, which is what I want. So everything here, this entire, the number of iterations here has polynomial dependence on the parameters of my problem. So ellipsoid is solving this problem in polynomial time, because these, every step to find the formula for this x bar and d bar, I gave it to you last time. It's a straightforward linear algebra operation. Okay, just involving some matrix multiplications and so on. Okay. Okay. So at high level, we are done. So claim that, so the theorem actually is ellipsoid method solves LP feasibility in time polynomial, the exact iteration, I mean, the exact complexity, I'm not interested in. But if you want the exact, what dependence, what is the polynomial degree, the book will have it. Okay, the exact dependence. But basically, time polynomial in n and log of u. Where what is u? U is that maximum entry of A, B, and C. Okay. Okay, so this was a very important result in 79 because essentially it showed LP can be done in polynomial time. Okay. Now, uh, there are some, okay, so I should note that I gave a very high level description. There are lots of specificities of the algorithm. Okay. So, for example, in this algorithm, you need to find a lower bound on the volume of the polyhedron. You need to deal with, uh, sometimes you might have irrational entries will show up because you square, so you have to do some rounding and so on. So there's a fantastic book by Lovash, um, Groschel and Schreiber, Groschel and Schreiber. This is sort of the classic. It's called Geometric Algorithms and Combinatorial Optimization. Okay, it's a fantastic book which will tell you all the details of the ellipsoid method. Okay, so if you ever use this later on in your research or you want to study more about this is the right reference to go to. Okay, it will tell you all the details and it will sort of, it doesn't look at this only for linear programming, it looks at it for convex optimization. Okay, but this is the reference. Okay. Okay, fine. Any questions about this before we proceed? Okay, so how do we do optimize? So I think last time you raised this question. We are talking about feasibility, but in optimization, we want to solve optimization problems. So what do we do? So I showed you one method, which is just use duality. Okay, so from LP feasibility, if I want to solve LP optimization problems, right? If I want to solve linear programming itself, okay, let's say from linear feasibility, I want to solve LPs. Can I use this algorithm? Okay. So there are two ways you can think about this. So one, which I told you last time is, so one way is one approach. So approach one, which is the use of duality. So you subject, let's say you're solving a primal and a dual. You just solve for the optimality conditions and the feasibility conditions. We know that X and P are primal and dual optimal if and only if some conditions are satisfied. Primal feasibility, dual feasibility, and strong duality expressed in whatever way you like. If you write it as complementary slackness, it becomes a nonlinear condition. But if you write it as the primal and dual objectives matching each other, that's a linear condition. Okay. So this is everything here is linear in X and P, my primal and dual variables. So this is a linear feasibility problem. So I would take the ellipsoid method and run it on this set of equations and inequalities. Find me an X and a P that satisfies these conditions. Once I do it, I'm done. If I cannot do it, it's infeasible. I cannot solve the problem. Okay. So that's one way. Okay. There is a second way, which is actually also useful, which is just run it in the primal space. Okay. So how you might do that is, so approach two, and there are a few ways you can do this, but here's one approach two. So let's say I'm trying to solve the primal problem. Okay, what are the things that can happen? So I first run, so here is the approach, run ellipsoid, and find X star satisfying AX star greater than equal to B if possible. Okay, so I just run the feasibility algorithm. Okay, I just check, find me a feasible point in the set. So what is going to happen? Ellipsoid is going to tell me it is empty, which means it's infeasible, or it is going to give me a feasible solution. So one of two things can happen. Okay, so we basically we deal with the infeasibility issue here. infeasibility here. Okay. Okay. Suppose it is infeasible, you stop the algorithm, you're done. You cannot find a feasible point. Clearly, you can't find an optimal solution. What is the second thing that can happen? If it is feasible, it might be that this problem is unbounded, optimal. Okay. So we can write that again as a set of linear conditions. How? Find D satisfying AD equal to 0 and C transpose D, let's say less than equal to some number. Let's say -1. Okay, you can set it to a number. Okay. So what is this doing? Okay. Actually, you can choose any number here. Okay. But what is this doing? I've got a point X star. Okay. If AX star, so I know AX star is greater than equal to B. Okay. I now try to find if I can find a direction. If AD is equal to 0, then XR plus D is a direction. Right? I can go in this direction D because AD is equal to 0. Okay. So I can move from X star, I can move to X star plus TD and I can keep increasing T. How does my objective function change? C transpose X star plus T C transpose D. Okay. So if this number was negative, for example, okay, or I mean, whatever this number is, if I can find some number where this is, let's say this number is negative, I can keep scaling T up, keep increasing T and make this problem unbounded. So I'm just basically finding a point in the null space of A. And if I can find a D satisfying this, essentially problem is unbounded. Okay. What is this? It's again a feasibility problem. I have to just find a D satisfying conditions. So again, run ellipsoid. I can go back to my feasibility algorithm and just apply it for this set of constraints, basically. Okay. I mean, you can use any number here because you can always, I mean, if this number is, I mean, basically it should be some number here which is non-zero, essentially. Okay. Is that clear or no? Any number here non-zero will work. Okay. Okay. Third, so if it is not unbounded, what we'll do is find a x satisfying ax greater than equal to b, and I'll try to just ensure that I decrease my objective function a little bit. For epsilon greater than 0, some small number. Okay. And repeat. Okay. So what is this doing? So I've got maybe so maybe I've got a point. Maybe that's my polyhedron. Okay. Maybe that's my ellipsoid. I'm sorry, actually I should, okay. Sorry. So I've got a point. Okay. I found some point x star in this space. Okay. I've already found x star which is feasible. Huh? AXR is, so this, if this is AX greater than equal to B constraints, I found X star feasible. All I do is, let's say my C is increasing in this direction. Okay. So this X, if this is C direction, this will give me a particular objective function. This is all C objective function is same along this point. All I'm doing is try to find me a point where the objective function is strictly smaller. Okay. So you try to find, but this is again a linear feasibility condition. So I should be able to apply ellipsoid again. Okay. And check if this can be done. If I can do it, I find a new point and then I decrease the epsilon basically. Okay. And if you do the search on epsilon carefully, you can run this thing efficiently. Okay. Okay. So you can do this in a couple of ways. I'm just showing you a couple of ways. One fully in the primal space, one in the primal dual space. Okay. Okay. Is the algorithm clear? Okay. Now the key thing which is important and sort of maybe the most important takeaway which I want you to take from the ellipsoid method is it has one very, very important property, the algorithm. If you look at the dependence of the ellipsoid method, even for the feasibility problem, okay, what is my feasibility problem? Ax greater than or equal to b. I've got m constraints, n variables. Huh? If you look at the complexity, it depends polynomially on n and log of u, which are the entries in A and B. It does not depend on m. So somehow it tells you that you can actually, the number of constraints in the LP somehow don't really matter. If you look at the ellipsoid method, if you look at the complexity of the algorithm, it does not somehow, I mean, there is no dependence on m anywhere. Why is that? Because you've taken some, no, what is the ellipsoid method doing? It's taking some polyhedron and sort of it's approximating it with good ellipses. Okay. And it's trying to find good ellipsoids. What is the thing about an ellipsoid? It doesn't have these sharp corners, which is what linear programming feasible region have. Okay. So what this tells you actually is that, so there is a very important result, what's called, so note, ellipsoid method has no dependence on m, number of constraints. So what is the implication? It means that there might be optimization problems with many, many constraints that you can solve efficiently. It might be possible. So just because you have a problem with an exponential number of constraints, you write many, many constraints, it doesn't mean the problem is hard to solve. Okay. So, so it, so the way you can implement, the way you can interpret this is, so there might be a chance to solve LPs with many constraints efficiently. Okay. And so we will try to formalize this next. Okay. So this is a very important result. It has a lot of implications. You can, you can use this actually. So this is what is called the equivalence of separation and optimization. Okay. It's a very important theoretical and useful practical result also actually. Okay. So let me tell you what this is. So here's a key. So equivalence of separation and optimization. So these are basically, the point here is that these are equivalent objects or equivalent ideas in some way. So I'll define what this is. Okay. So what's a separation problem? Okay. So optimization is easy. Okay. So what's an optimization problem? Of course, we are in the linear space. I mean, we are in a linear programming world. So given a polyhedron P, optimization is very simple, and a vector C in Rn, what we have been doing for the last 10 weeks or 9 weeks, find X star in P that minimizes C transpose X. Okay, that's my minimizes C transpose X over X in P. Okay, so that's my optimization problem. Okay. Okay, so that's a linear optimization problem. I mean, what we have been spending all our time doing. What is the separation problem? If I give you a polyhedron, so given a polyhedron P, so let me first write it down, and a vector X star in Rn. Okay, it may not be in P. Okay. Either, so do the following. Verify if X star lies in the set. Okay. And if it does not, lie in P, find an inequality or what is called a separating hyperplane. Separating hyperplane A transpose X greater than or equal to B, that is satisfied by all X in the polyhedron and violated by X star. Okay. So that's what's called a separation problem. Okay. So let me tell you what this looks like, the separation problem. Suppose I give you a polyhedron. Okay. So what can happen? Of course, X star can be in P. Okay. Okay. So if you verify X star in P. Okay. Okay. The other thing which could occur is X star lies outside P. So it does not lie in the set. What I require you to do in this case is find me an hyperplane. So that's a linear inequality. So that this condition is satisfied by every point in the polyhedron, but clearly A transpose X star is lesser than B. It's violated. So this is called a separating hyperplane, a hyperplane that separates a point from the feasible region. If you can do this efficiently without without checking each. So there are many ways you can do it. Okay, one way you could do it is you could say, okay, you take this point. For example, this point violates this constraint because this constraint is what is going in this direction. Okay, so this could have been a separating hyperplane because this constraint is what? This constraint is in this direction, right? This could have been a separating hyperplane. It would have separated my polyhedron from the point. But ellipsoid method doesn't require that. You can choose any separating hyperplane. You can choose any way to cut off the point from the polyhedron. Okay. So and this is sort of a very important result in optimization, not only in linear optimization, but in convex optimization theorem. Optimization is solvable in polynomial time, solvable in polynomial time. What I just discussed, if and only if separation is solvable in polynomial time. So if you can do this efficiently, this step, if I can do this step, check if a point lies in the polyhedron quickly, and if it is not lying, find a separating hyperplane quickly, then I can solve the separation problem efficiently. And it turns out you can then solve the optimization problem efficiently. Because the reason is very simple, that what the ellipsoid method requires is, it just requires you to find a separating hyperplane, a way to separate a point from the polyhedron. It doesn't require anything else. I mean, of course, it requires the steps, but that's the key step, basically. Okay, is that clear? It turns out to be very useful. You can write many research papers using this idea. Because if you understand this idea, you might take an optimization problem, you might look at it, and it might look initially like a very complicated problem. Many, many constraints, exponentially many. But that doesn't mean it's solvable, it's hard to solve. It might just be that you've not thought about the problem in the right way. You might have to transform the problem, or you might have to do something else. Okay. So I'll show you a couple of examples of this idea uh, where it is useful. Okay. Okay. Is the result clear? You can ask questions if there are any. Actually, this also works for convex optimization. So you have written it for a poly. I mean, there are some additional. There are some. You require some other additional technical conditions, but largely you can do the same trick. Even if you have a convex body, if you can separate it using if you take a point, you can check if the point lies in the convex set. Otherwise, separate it. Find a linear cut, a separating hyperplane which separates it. If you can do this efficiently, you can essentially solve convex optimization also efficiently. Okay, with modulo some technical details. Okay, but the key idea is the same. Okay, so I want to show you a couple of examples of this. Okay, but is it clear the result? Do you see the difference between finding one hyperplane and using this hyperplane? The challenge in the polyhedron is what? There can be many such constraints. So I might have to check each one of them and enumerate all of them. If there are too many constraints, exponentially many, defining the polyhedron, that's a bad idea. Okay. So let me show you two examples to illustrate the usefulness of the idea. Okay. So I'm just going to show you two examples. There are actually many more examples. Okay. So let me show you two examples. So the first is something called the minimum cost. Basically, it's a directed spanning tree, which is what is called a arborescence. Okay. So I'll tell you what this. So this is a graph object. It's basically a directed tree. Okay. So what is this? So I'll explain this problem. So given a directed graph, okay, with some costs Cij non-negative for every arc in the graph. Okay. And let's say there is one special node. Okay. Uh, a special node, let's call it R. So there's one specific node in this graph. Let's call it R. Okay. The goal is what? To find a minimum cost arborescence. So what is arborescence? So I'll describe this here. It's basically a directed tree that is rooted at R connecting to all nodes. Okay. Okay. So let me show you an example. So here is let's say a graph. Let's say this is node R. Okay. There are many edges in this graph. Maybe it's a complete directed graph, order n squared edges. Okay. So what's an arborescence? So for example, this is an arborescence. Okay. So R may be connecting here to this node, maybe connecting here, maybe uh, connecting here. Okay. And maybe connecting here. Okay. So that's a arborescence. So directed tree, which starts at, it's rooted at R, and there's a path to get to every node. Okay. There are many such directed trees you can find in this graph. So here's another one. So maybe this is a, so this is a long path basically. That's also an arborescence. So directed tree which starts at R, and you can actually visit every node in this graph. The question is, you check all of these arborescences and pick the smallest cost one. That's the objective, because what is the problem? The problem is there's a cost on every arc. Okay, there's a cost on every arc. So this will have a different cost compared to this because you're using different edges. Okay. Find the one with smallest cost. Okay, is the problem clear? So it's basically like a directed tree. Okay, that's it. Okay, rooted at R. That's a problem. Okay. So if you have some important node, you want to connect to everything else. So you want to get from this important node to everything else in the best, with the cheapest cost spanning tree. But there's a sense of direction here. Typically in spanning trees, there's no sense of direction. Okay. Okay. So let's first write down an optimization problem for this. Okay. So here is a formulation. Okay. So the natural variable is what? Xij. 1 if ij is used if ij is part of the solution, and 0 otherwise. Okay, if I don't use the arc. Okay. So in this case, all these arcs are 1, everything else is 0. Yeah, these are 1, everything else is 0. Okay. So here is we will write down first an IP formulation. So I want to do what? I want to minimize summation over every edge in the graph, Cij, Xij, subject to, okay, so I have to keep track of the fact that there's a directed spanning tree. Okay. There are some ways you can write this. So one way you can write it is what? You take any subset of nodes which contain, so what should this, okay, so clearly Xij has to be 0, 1, okay? So that is it. Okay. The key step is this fact that there's a directed spanning tree. Okay, so what does it mean for there to be a directed spanning tree? You take any subset of nodes that contains R. So if you have R and you take any subset of nodes that contain R, let's say I take a subset, these subset of, let's take any one subset. Let's take this subset. If I require there to be an arborescence, I have to ensure that in the solution for the edges which go outside this set, there has to be at least one edge going out of the set because I should be able to get to nodes which are outside the set. Otherwise, it cannot be a feasible solution. I will be disconnected. So you take any subset of nodes in this graph, you should have a way to get outside that set because one of the edges going out has to at least be one. Otherwise, you are stuck. You will have a cycle within this and you cannot go out. Okay. So these are what are called typically cut set formulations. So the constraint is the following: summation xij. Okay. I lies in a set, let's call this S. Okay. J lies in the set not in S. Okay. This set has to contain this node R. Okay. I have to ensure that at least one of this has to be non-negative for every subset of V where S contains R. Okay. Clearly, I require this for every strict subset. You know, if I take the entire set of nodes, I don't want there's no edges going out of the set. Okay. So this is for every subset. That is a formulation. In fact, it's an exact formulation for this problem. Okay. So is it clear what this constraint is doing? The star constraint is. Is it clear? Huh? Okay. Now, what are the problems in this formulation? There are two problems. Okay. One is it's an integer program. Okay. Okay. Integer programs are going to be harder to solve than LPs in general. Okay. Um, okay, that's one issue. The second is even if I was to relax, okay, this problem. So suppose I take this. So what's an LP formulation? In the LP formulation, I would just simply say forget the integer variables and simply write this as xij between 1 and 0. Okay. That's maybe the simplest way you can do it. You say, I will just forget integrality. I will say everything is between 0 and 1, and I will just solve the LP problem. It turns out actually the LP relaxation here will be tight for this problem. But let's say I solve an LP. There is a second source of a problem. What is the problem? The problem is I am checking for every subset of node in the graph. So if I give you 100 nodes, this is what? 2 to the power 100 roughly. This is roughly of the order of what? 2 to the number of nodes in the graph. So if my graph grows up by 10, this grows up exponentially. Basically, as V increases, my number of constraints grows exponentially in this. So solving this LP for large number of V is a non-trivial task. Just inputting the LP is exponential size. Okay. Is that clear? But I claim that this problem can be solved efficiently because separation can be done efficiently. Okay. So what is the separation problem for this LP? Okay. So if I think of it as an optimization problem, it looks hard. It's exponential size input. Okay. What is separation? Separation says, so let's write down the separation problem. So here's the separation problem. Given x star, xij star lying between 0 and 1 for every edge in the graph. Okay, so remember the constraints which are not too many, like polynomial number of constraints, I can put it in explicitly. My only problem why this LP doesn't look immediately solvable efficiently is the fact that I've got many constraints. Like these constraints are easy to deal with. They're just upper and lower bounds of 1 and 0. So suppose I force these constraints in, that's fine. Okay. So given some point x star which satisfies these constraints, but what I want to check is check if x star satisfies these additional constraints, this constraint star, it's a set of 2 to the power v constraints roughly. And if it does not satisfy it, find a separating hyperplane. That's the separation problem. Okay. So you will see in many optimization papers where they have these type of exponentially many constraints, they will formulate what is called the separation problem. Okay, it'll be of this type. Basically, it's saying, suppose I give you a point. These constraints are easy to deal with. I want to check if that point satisfies all these constraints. And if it does not satisfy it, find me a way to cut off that point from the feasible region. Okay. Of course, the trivial algorithm is just check each of these constraints, but I don't want to do that. That becomes a naive way to do this. I don't want to check every subset. Then I go back to the old problem and I enumerate over every subset. So how can I do this efficiently? The idea here is this is like a cut. Okay, so here is the idea. What do you want to do? Okay, to solve this, so you've got a, let's say a node, let's say this is R. You've got nodes, let's say in the same graph. Or, it doesn't matter what the graph is, okay? But let's say you've got nodes, okay? You've got edges coming out, maybe coming in, it doesn't matter. Okay, so you've got values xij on every edge given to you. Okay. Okay, what do you want to check? You want to check the right hand side here is 1. Okay. So what is this telling you? You want to check what is. So what you want to solve is the following. You want to minimize summation xij star for I in S, J in V not in S. Okay, where S contains R. You want to minimize this. Sorry. Sorry, just give me a minute. Ij in E, every subset of V, S contains R. Okay, so what am I doing? If I give you xij stars values, I want to check if I minimize this number over every set containing R, subset of V, if it is greater than or equal to 1. If I can solve this problem efficiently, by the way, I think I should have added here Ij and E. It's only for edges in the graph. Okay. I want to be able to calculate this number efficiently. If I can calculate this number efficiently, what happens? I basically, if this number was greater than or equal to 1, I'm done. If it is less than 1, essentially some constraint is violated. How do I solve this? This is nothing but a set of V minus 1 minimum ST cut problems. Okay, so what are we doing here? Trying to find, you go from R to, let's say, a particular, you want a set S which contains R. Okay, so let's say you're going from R, let's say this is my ST cut, let's say this is node S, let's say this is node T. Find the minimum cut where xij stars now are the capacities. Find the minimum cut from R to 1, R to this, let's call this node 1. Okay, so from S to 1, find the minimum ST cut. From S to 2, find the minimum ST cut. Each time you find the minimum ST cut and pick the minimum of them. Okay. Is it clear? What is this doing? This is just creating a what is this problem doing? It's just creating a cut, right? A cut which contains a node S, which contains a node R. And the other side can be anything. So I'm just trying out different sync nodes. I have got a total of V minus 1 sync nodes. For each of them, I find the minimum cut. I find the minimum ft cut and I pick the minimum of this. But what is minimum ft cut? That's an easy problem. That's network flow. We studied max flow min cut. This is solvable in polynomial time. So if I find the minimum cut, if the entire number was greater than equal to 1, my x star lies in the set. If it is lesser than 1, the cut will give me a separating hyperplane basically. Okay. So since this is solvable in polynomial time, so since separation is polytime, it implies solving the optimization is polynomial time. So we looked at a problem, it looked to be hard, but separation is easy for this problem. So actually optimization is easy. So you can actually use the ellipsoid method or you can use some transform formulations to solve this problem. Okay. So the point here is just because a formulation looks like it's got exponentially many constraints, it doesn't mean the problem is hard. You have to analyze the problem. You have to think creatively and look at what is the underlying structure of the problem. In this problem, the underlying separation problem are min cut problems. And min cut is easy to do. We've seen this with LPs, network flow. Okay. So one important trick in optimization is to, once you understand different classes of problems, only then you will be able to understand if some problem can be transformed to some other problem or no. That's why we're trying to learn different classes of LP or IP problems. You know which is easy, which is hard. You learn something is easy. Maybe your existing problem can be transformed to that problem. Okay. Okay. So that's one example. A second example is I'll just show you one more example and then we'll take a, give me 5 more minutes, then we'll take a break. So a second example, just to illustrate the idea. This is actually not a linear optimization problem. It's a semi-definite programming problem. Okay, SDP, semi-definite program. Okay, it's a very important class of optimization problems. Okay, so what's a semi-definite program? So last time I defined to you what's a positive semi-definite matrix. Okay, so remember a matrix X of size n by n, if it's positive semi-definite, what does it mean? It means that like V transpose XV is non-negative for every V in Rn, or equivalently, all the eigenvalues of X are non-negative. That's what's a SDP matrix. So what's a semi-definite program? It's an extension of linear programming. Okay, so it's a problem of the following type. X is now a variable. Okay, so you want to minimize some linear function of X. Okay, so I don't want to get into matrix notations here, but some linear function of the entries of X. Okay, so you take maybe the first entry, the second entry, you add it up or whatever, some linear function subject to linear constraints on X. So this is like LP problem. The only change is my decision variable here is a matrix X, which is positive semi-definite. Okay, so this is what is called a SDP. It's a generalization of linear programming over matrices. So far, we have been optimizing over vectors. This is an optimization over a matrix. Okay, it's a very important class of problems. Okay, many problems can be modeled as this. Okay, and you can take a full class just on convex optimization and semi-definite programming. We won't go there. Okay, so I claim that these classes of problems can be solved in polynomial time too. Okay, how? Okay, so first thing to observe is these are linear constraints as a convex set. This is a convex set. Okay, why? This is a convex set. Okay, why? If I give you two matrices, x1 positive semi-definite and x2 positive semi-definite, it implies lambda x1 plus 1 minus lambda x2 is also positive semi-definite for every lambda between 0 and 1. That's a definition of convex sets, right? I give you 2 points in the set. A convex combination of the 2 points should also lie in the set. Okay. Why is this the case? What is the definition of convex of PSD? V transpose x1 is, the definition is V transpose x1V is non-negative for every V in Rn. And V transpose x2V is non-negative for every V in Rn. If I want to show this matrix is positive semi-definite, I have to take V transpose lambda x1 plus 1 minus lambda x2V And now I have to simplify this by expanding. So take lambda out, V transpose x1V plus 1 minus lambda, V transpose x2V. But lambda is non-negative because lambda is between 0 and 1. 1 minus lambda is non-negative because x1 is positive semi-definite. This number is non-negative. This number is non-negative. So I'm adding up non products of non-negative terms. So this has to be non-negative for every V. So that's a convex object, basically. The set of positive semi-definite matrices is a convex set. Okay. Okay. Now it turns out you can think of this as a linear program, but in infinite dimensions, because I could have written this constraint as V transpose XV greater than or equal to 0 for every V in Rn. Okay. So this is optimization over the variable X. Okay. X is a variable here. So this is actually a linear. So this is actually a linear object in X. Okay. It's quadratic in V, but if I'm enumerating all V in Rn, which is an infinite number, of course. Okay. So this is actually not exactly a linear program. It's what's called a semi-infinite linear program. There are infinite number of constraints. Okay. But the theory of ellipsoid method goes true for convex optimization too. Okay. So let's ask ourselves, what's the separation problem here? So separation here is what? Given X star, test if X star is positive semi-definite, and if not, find a separating hyperplane. Okay. Okay, dealing with linear constraints is easy. I'll just use linear constraints. My problem is this constraint. There are basically infinite number of constraints here. Okay. But to check if a matrix is positive semi-definite, I don't have to actually check this. What I could have done is I could have simply calculated the eigenvalues of the matrix. Okay. So this is easy to do because so if I give you a matrix of size n by n, you can calculate eigenvalues using linear algebra basically. Okay, so order n cubed operations. Okay, because finding eigenvalues of a matrix is easy. Finding eigenvalues can be done in polynomial time. Okay, essentially in cubic time. Okay, so I can find eigenvalues efficiently. I find all the eigenvalues. If they're non-negative, the matrix is positive semi-definite. If an eigenvalue is negative, the corresponding eigenvector will give me a separating hyperplane because V transpose XV will be like lambda times the this is eigenvector lambda times V. So V transpose V, if this number is negative, this number will be negative. Okay. So it will violate this constraint. So it will give me a separating hyperplane. So what this tells me is separation for SDP is easy, which means optimization for SDP is easy. So it turns out that this class of problems can be solved in polynomial time. Again, using the idea of separation. You don't have to enumerate every constraint. Okay. You don't have to write it this way. You have to just check if a matrix is semi-definite. That can be done using just eigenvalues, basically. Okay. So I wanted to give you two examples where a problem might not look immediately easy to solve, but if you have the separation, if you have that hat of understanding what a separation problem is, you can see it to be easy. Okay. There are many problems involving like probability and optimization where you can do this. In fact, I have a book where I've discussed this for moment problems and for DR robust optimization problems. Okay. So it's a very powerful technique. Okay. So I just wanted to introduce the technique to you. So the point here is ellipsoid method is useful. It may not be very practical, but it lets you identify problems which are easy to solve in polynomial time. Okay. Not every problem can be like this. Of course, there are problems where the separation can be hard. Okay. It doesn't mean that every optimization problem with exponentially many constraints is easy to solve. If you analyze the problem, it might be easy to solve. Okay. Okay. It's 11:10. Let's stop here. We'll take a 5-minute break. I'll spend the last 45 minutes just giving you the idea of the interior point method. Let's stop. We'll take a 5-minute break.
What is hello, welcome people. This one you need sleep. No, I'm sick. I feel sick. Oh, okay. I gotta go to the doctor. Right. You feel sick after you see. I think. Okay. Okay, you guys are. My score is like Manchester United's performance. Oh my god. If you think it's good, if it's good, draw. Draw a lot. My score, draw. Excuses. I think that was
Yeah, I think this one it's only for if it is strictly positive Li, right? So Li has to be if Li's are like everyone will not be necessarily zero, and because the Li's might some of the Li's might be zero or one. Some Li's might be so there might be some positive. If all Li's are positive, that's fine, but not all Li's have to be strictly positive. Some Li's could be zero.
Yeah, but even if some of them are zero, everyone says to one, right? So
That is fine, but there will be so for each of them to be strictly.
oh yeah, yeah.
So it's not necessary that everyone has to be zero. So I'll tell you how to. We can basically write down a dual formulation to show this. So I will discuss this. I'll discuss this maybe in week 13 or so. Yeah, I'll try to see when I. Okay. Okay. Shall we start? So, because I'm going to just spend about 45 minutes just trying to introduce interior point methods. Okay. Again, my goal for doing this is to ensure that at least you have the key idea of the algorithm. We will not be able to go through in detail for the algorithm again. Okay. Uh, but it's important, at least I think you should at least see the method once to understand what the method looks like, because it works differently to simplex and ellipsoid. Okay. 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 So here is okay. So the main idea, which so this was initially developed by Karmakar in 1983. There was a lot of work before that, and for about I mean, there's quite a lot of development on these methods for the last 30 years, 40 years. Uh, so the idea is when you're looking at the linear programming problem, in the simplex, you go along the boundary. In ellipsoid, you use some ellipses to approximate the set and try to reduce the size of the ellipsoids. In the interior point method, you try to not go along the boundary of the set, but try to find a way through the interior of the set. Okay. So you'll have to then appropriately describe the problem to do this and to make it work. Okay. So let's take an optimization problem. Let's take a standard form LP. Okay. And so the key idea is to uh, transform the LP to only equality constraints. Okay. And use what's called a barrier function and use a barrier function to try and prevent variables from taking a value of zero. Okay, of course, some variables will take a value of zero. Okay. I mean, remember, in standard form, you'll have non-basic variables and you'll have basic variables. Non-basic variables will take a value of zero. Basic variables will take a positive value. Okay. Or it should take a positive value if it's non-degenerate and so on. But we will try as much as possible to ensure the variables don't go close to zero. Okay, and what is the logic? The logic is that the problem is when the boundaries are when particular variables are going to zero, like a slack variable or something like that. So you try as much as possible to stay away from the boundaries. Okay. Of course, it has to work and solve the original LP problem. My ultimate goal is to solve this problem. Okay. So how do you do this? Okay. So you create something called a barrier function. Okay. So I'm going to first define the barrier function. So here's a barrier function. So define a barrier function. It's parameterized by a non-negative number u. Okay, in the following way. You take the original objective function C transpose X minus mu times summation J going from 1 up to n log. And this is natural log. Okay, everything here is natural log. Okay, log to the base E. Okay. Okay, and what we are going to try to do is we are going to try to. So here's the algorithm. Try and minimize so try and solve the following problem. Minimize bu of x over the constraints ax equal to b, okay, and keep changing mu. the parameter mu from infinity down to zero. Okay, and I'll explain the logic. Okay. Okay, so that's the basic idea. So you take a linear programming problem. The first thing you should observe is it's taking a linear optimization problem and it's making something non-linear. I mean, clearly log is a non-linear function. Okay, so somehow it's adding in some non-linearity to make the uh, problem behave somewhat differently. Okay, okay. So is that clear? Firstly, what the problem is? Okay, and so what is going to happen is it will turn out that the limit of the optimal. So let's say the optimal solution here is x star. Okay, for the LP. Okay, for simplicity, think of it as a unique optimum, but let's say it's fine. Okay, the optimal solution x star. This is going to be an optimal solution x star, which is parameterized by mu. Okay, mu is a parameter. Okay, think of mu as some fixed number. Okay, I'm going to change mu in the algorithm, but for a fixed mu, I'm going to solve this problem. If I could solve it for now, it'll turn out the limit of this solution x star of mu as mu goes down to zero from infinity. So mu starts as a large number and then goes down. This will converge to x star. So solving a sequence of parameterized problems will converge me to the original LP solution. Okay. Okay. I mean, okay. So is that broadly clear? Okay, we'll explain what happens exactly. Okay. For each different mu or exactly, you have to solve it for different mu, you have to change mu, and actually you won't even solve it exactly. You will solve it using a Newton's method. I will explain that. Okay. Okay. So let's first. So okay. So what's going to happen is you're going to start with some mu. You're going to solve the problem. You're going to change mu and roughly solve the problem. And keep repeating this. Keep trying to decrease mu till you are guaranteed to have an optimal solution as mu goes to zero. Okay. Okay. So let's first look at a few. Uh, okay. So few. Okay. So first a few properties. Okay. So the so few properties. Okay. Just to I mean this is easy to see, but the key function here is minus log of x. Okay. That's a function, right? Minus log of x. So what does this function look like? Okay. So if you look at this function, okay. So log of, so if this is x, the log function is defined only for positive numbers. Okay. So this is log of x, where log of, and then this is, so this will be log of x. It's an increasing function. Okay. This is minus log of x. Okay, it's a decreasing function. Okay. Okay. This function, technically the log of x is only defined, f is only defined from the positive domain. Okay. It's only defined from the positive domain, right? I mean, logs only defined for strictly positive numbers, basically. Okay. So what we can do is, if we want to, because in this problem, we are going to we are not, in the original problem, x is non-negative, but I'm taking out that constraint here. So I'm thinking of x being arbitrary here. So what you can do is you can simply, so we can define, so one thing we can do is we can define f of x to be plus infinity if x is 0 or less than equal to 0. Okay. So I'm just trying to define the domain on the entire R space. Okay. Remember, I'm trying to minimize functions. Okay. So if you make a function go to plus infinity, that's the worst thing for minimization. It's basically infeasible, right? I'm trying to minimize things. So if this number goes to plus infinity minus log of x, I mean, that's the worst thing which can happen. Okay. So it's going to force the x not to go to a 0 or a negative value. So I'm trying to minimize this function. Okay, fine. So what happens is the corresponding function now is defined from R all the way from all real numbers to R and its union with, so at this point I made it like infinity. Okay, so this is like plus infinity all the way out. Okay. Okay. So I've defined f on the entire R now. Okay. It's plus infinity here, and then it decreases. Okay. Okay. 2. Okay. What is the derivative? The derivative of minus log of x is minus 1 by x for x positive. Okay. And the second derivative is obviously 1 by x squared when x is positive. Okay. So what is this function? So f is strictly concave. Sorry, f is strictly convex. Minus log of x is strictly convex. It's got this property, strictly convex and decreasing on the domain on x positive. Okay. Okay. Fine. Straightforward. Huh? Okay. So what does this means? If f is strictly convex, this problem, when I'm minimizing, minus log of x is a convex function. So this actually is what is called a convex optimization problem. Right? It's a convex program. So remember what's a convex program? We did this like in the first week. We're minimizing convex functions over convex sets. Okay. This is actually a linear set. It's a convex function. Okay. So it's a well-defined function which is convex, which you're trying to minimize. That's a good thing to have generally. Okay. Local minimum is global minimum. Okay. Okay. Now to analyze this, I require to introduce optimality conditions for nonlinear optimization. Okay. So, uh, so I want to introduce to you what are called Karush-Kuntaka conditions. These are like the optimality conditions for nonlinear optimization. So we have studied this for LPs. I want to generalize this to nonlinear programs because like we are going to look at a nonlinear program. Okay, again, these are very useful conditions to know. Okay. Okay. So let's take a general optimization problem of the following type. I've got a nonlinear function. I've got nonlinear inequality constraints. And let's say I've got some equality constraints. Okay. And let's say X is an Rn. Okay. So this is a very general nonlinear program. It might not be, I mean, it doesn't have to be, it could be linear. Linear programming is a special case of this. This is very, very general class. Okay. Okay. So what are the KKT optimality conditions? So what are the KKT? Karush Kuntaka. These are the name of 3 people who develop these conditions, which are very useful to know. Okay. So what are the KKT conditions? Essentially trying to capture what an optimal solution would look like. But of course, this is a general nonlinear program. Nonlinear program. Finding a global minimum for a general nonlinear program is a hard problem. Okay. Regardless of what people might believe. Okay. In general, nonlinear optimization is a hard problem. Okay. It's not a trivial problem. Uh, okay. Unlike LPs. Okay. Okay. So what are KKT conditions? Okay. First, sorry. So these conditions actually, the first set of conditions are, it's a great, okay. So of course, we're assuming here everything is differentiable. Okay. NLP, I'm going to assume everything here is differentiable. Okay. So the gradient of the objective plus there'll be a dual multiplier. Let's call this UI and VJ. Okay. Plus summation I going from 1 up to P. So let's say X star. So X star, there are going to be a set of variables X star, which are the primal variables. There's going to be U star and V star. Satisfy the following. These are the KKT conditions. The gradient of F plus UI times the gradient of G. So this is a gradient derivative basically. Okay, it's a vector. It's a column vector. Okay. Plus Vj times the gradient of H. These gradients have to line up. They have to give me a value of 0. Okay. If I take the derivative of the function f with respect to each variable x1 up to xn, likewise for g and likewise for h, and I take a multiple times those gradients, they have to line up. So this is gradients lining up. You have primal feasibility. Dual feasibility. Primal feasibility still. And then you have essentially complementary slackness type conditions. So you have conditions like ui. Okay, firstly, the dual variables have to be non-negative for the less than equal to constraints. They are free for the equality constraints. And then you have complementary slackness type conditions, which basically says that ui star times gi x star is equal to 0. Okay. So if you think about linear programming, this is essentially primal feasibility. This is dual feasibility. Okay. Primal feasibility, this is essentially going to be dual feasibility along with these conditions plus complementary slackness. Okay, you can take a LP and just compute these derivatives out, and you will find that it's exactly that. Okay, but let me try to provide you some intuition for this. Okay, so is it clear what the conditions are? Okay, so if I find X, V, and U which satisfy these conditions, they are said to satisfy KKT conditions. Okay, why are they important? They are going to be, okay, so first is if X star is a local minimum, X star is a local minimum of nonlinear programming, of NLP. So if I've got a point which is a locally, it's the optimal, in a local domain, it is optimal, okay? And uh, they satisfy something called Slater's condition. I'll explain what Slater's condition is. So there's some regularity condition, okay? So what is Slater's condition? For example, there is some point which is strictly feasible in this domain, okay? So I mean there exists some x bar such that gi x bar is strictly negative and hj x bar is okay. So what is this condition saying? It's basically saying that if you look at this feasible region, there is some point which is in the strict interior of this feasible region. So there is some feasible point where this was satisfied with strict inequalities and this equality. Okay, so there's some so this is called Slater's condition. Then uh, basically there exists u star and v star such that this x star, u star, and v star satisfy KKT conditions. So local minimum, if I got a point which is local minimum and the optimization problem satisfies some regularity condition, essentially you can find that is the point has to satisfy these KKT conditions along with these variables u and b. Okay, so these are what are called necessary conditions for local minimum. Okay, so let me give you just the intuition of this. So imagine I've got an optimization problem. So intuition, why should you believe these conditions? Let's say I've got an optimization problem. Okay, so maybe this is g1 x less than equal to 0. Maybe this is g2 x less than equal to 0. Maybe this is g3 x less than equal to 0. Okay, so I've drawn curves here because these are nonlinear programs. Okay, I've not drawn like lines, right? Like what I did. I've not drawn hyperplanes here because they're NLP. Okay, so what is a feasible region like? It's basically all the points in this intersection of these sets. Okay, agree? Okay, in this example, I've not drawn any equality constraints. That's fine. Okay, okay. I'm trying to minimize some function. Okay, so let's say my function, let's say the minimum point of this function, if I had no constraints, is this point. Um, so this is the global minimum of the function f. All the points here have f of the same value. So these are what are called so every point along this curve has the same objective function. Okay, so I would have liked to choose this point, but this point is not feasible. Okay, so what is the minimum? The minimum for this problem will be when this point, when these curves touch the feasible region first, which is in this place. Okay. So imagine what does the gradient look like? So these are my objective function is increasing in this direction. Okay. So my gradient at this point, so if this is x star, if this point, let's call this point x star, what is this? This is del of f of x star, right? The gradient is increasing in this direction at this point. Okay. At this point, what is G1 is active. What if del G1 of x star? Basically, del G1 of x star will line up in this way. This is del G1 of x star. The direction, I'm sorry, this is not G1, this is G2 in this example. This is G2 of x, so this is G2. The gradient of G1 at x star really does not matter because this one, how G1 looks like, even if I was to change this curve a little bit, if I moved it, it doesn't change my optimal, my x star being the optimal. Okay. So what that means is, so what is my condition? My condition is del of f of x star plus u2 del g2 of x star has to be equal to 0. u1 del g, so u1, which is the dual variable for where this u2 is non-negative. This condition says u1 times del g1 of x star is equal to 0, but g1 of x star is is not tight at this constraint. So u1 is actually 0 in this example. Okay. Likewise, u3 will be 0. Sorry, this was g1. So I think I wrote g1 two times. Huh? This is g1 and this is g3. So u1 and u3 have to be 0 because the gradients are not tight. They are not, these constraints are not active at that point, basically. Right? Sorry, this should be u1 times g1 of x star. G1 is not the constraint is not tight at x at G1 is not tight at x star, so the corresponding dual variable has to be 0. What is this saying? The gradients line up basically. Okay, so that's KKT. Okay, so it's very natural. Okay, except it's working with the gradients. For linear functions, the gradients are constants. Of course, for nonlinear functions, the gradients are not constant. Okay, now it turns out, why do you require this Slater's condition? Without Slater's condition, you can have some funny things happening. So do you require Slater conditions? Do you require Slater's condition? The answer is yes. So for example, if I give you a problem like this, minimize x1 subject to x1 squared less than equal to x2 and x2 equal to 0. Okay. You look at this problem. This is x1 and x2. It's got a trivial optimal solution. x2 is 0 and x1 is equal to 0. Okay. There's actually only one feasible point. In this problem, there's one feasible point. That's the optimal point. If you write down the KKT conditions for this problem, it will be gradient with respect to x1 and x2. So that's 1 and 0, del of f of x plus u1 times, so there's a single u here, gradient with respect to x1, that's 2x1. Gradient with respect to x2, it will be x1 squared minus x2 less than equal to 0, so that's minus 1, plus v times gradient with respect to x1 and x2, that's 0 and 1, equal to 0, 0. What is the first condition telling me? 1 plus u2x1 equal to 0. Okay. Okay. If x1 is equal to 0, condition is violated. This cannot occur, right? If x1 is equal to 0, clearly 1 is not equal to 0. There's a violation. So something went wrong. The KKT condition didn't work. Because KKT works only when there is some regularity in the feasible region. You require something called constraint qualification. Slater's condition is a type of constraint qualification. There's some other variants of this. But you require, I mean, the point is you require some additional property like strict feasibility or something like that for this to work. Okay. Okay. So that's KKT. So this is what is called necessary conditions. So if I got a local minimum, it's necessary and Slater's condition, it has to satisfy this condition. It turns out when the problem is convex, so sufficiency, so if F is convex, Gi are convex, Hj are affine, so linear function. So I've got a convex program. Okay, I'm minimizing a convex function over convex feasible region. Then plus KKT conditions are satisfied. X star is optimal. So there's actually a reverse direction under convexity. Okay. So the first set of conditions was necessary. This is sufficiency basically. So under convexity, if you find a point that satisfies KKT conditions, that's optimal basically. Okay. Okay. So we're going to use this. So I'll look at the KKT conditions for the barrier problem. Okay. Okay. So we're not going to prove KKT, but one way, if you're seeing this I mean, you probably are seeing this for the first time. You can go back and look at some nonlinear programming books, or you can just try to apply KKT for linear programming. Compute derivatives, you'll find that KKT is exactly primal dual feasibility and complementary slackness or strong duality. It's exactly that, but generalized to nonlinear optimization. It gives you so Slater's condition, and so it gives you necessary conditions under this KKT, under this Slater's type condition, and it is sufficient under convexity. Okay. Okay. So now let's go back to the barrier problem. Okay. So I want to minimize C transpose X minus mu summation j equal to 1 to n log of xj subject to ax equal to b. Okay. This is what is called the barrier problem. The primal parameterized by mu, where mu here is a fixed number positive. Okay. So this is a convex program. Okay. Okay. If I write down KKT conditions for this problem, okay, now there's a corresponding dual problem, okay, which will be maximize P transpose B subject to P transpose A equal to C transpose. Okay, sorry, P transpose A plus S transpose equal to C transpose plus mu times summation J equal to 1 up to J log of Sj. These are the dual slack variables. Okay. This is the primal and this is a dual. Okay. Okay, fine. So here is a theorem. How does the optimal solution look like? Okay. So X star is primal optimal. And P star and S star are dual optimal. Okay. If and only if they satisfy the following conditions. Okay. First, primal feasibility. A times. So I'm going to call the A times X star. I'm going to call this X star of mu equal to B. It's okay. The optimal solution will depend on mu. Okay. The optimal solution will depend on mu. Okay. A star, so I can parameterize everything by mu. So one, primal feasibility. Two, okay, next is the optimal solution. X star has to be non-negative. The minus log of X will force it never to become negative or zero. Okay. So X star mu will be always non-negative. In fact, it will be strictly positive for all mu positive. Okay. Three, P mu transpose A plus S of mu transpose is equal to C transpose. So that's sorry, S non-negative is required here. 4, S mu is non-negative. And 5, complementary slackness in this problem will look like X star of mu times S star of mu is equal to mu for every variable. Okay. So remember, this is exactly primal feasibility. This is exactly dual feasibility. The only thing which has changed compared to standard linear programming, when I write standard primal dual LP, I would have had the same primal and dual feasibility conditions. The only thing that has changed by doing this parameterization with the barrier function is this condition. In linear programming, I would have complementary slackness. The primal variable times the dual slack or whatever x times s will be equal to 0. But here, x times s gives you a number mu. Okay. This is the only difference compared to the classic primal dual optimality conditions. It's in this condition. Can you see that? Or no? If I take a linear, if I solve ax equal, if I solve a linear program, minimum, no, what is primal feasibility? Ax equal to b, x non-negative. What is the dual? It's maximize p transpose b, p transpose a less than equal to c transpose. I can add a slack. That's my primal and dual feasibility, right? So I've just written down here primal and dual feasibility actually. What has changed is in classic LP, x times s is equal to 0. There's complementary slackness. Here, complementary slackness is showing up as the product of these two variables is equal to mu. It's not equal to 0. Okay. But you can see what will happen as mu goes down to 0, this number will go down to 0 basically. Okay. So how do you see this? You can just take the KKT conditions for this problem, right? What is the so why should you believe this optimality conditions? So what is KKT telling me? KKT tells me, so apply KKT. What is KKT? Take the derivative with respect to any variable. Let's say the jth variable, I'll get Cj, okay, minus mu times the derivative with respect to xj. Log of xj derivative is 1 by x. So it's mu by xj plus p transpose plus, I mean, because p is a free variable, so minus p transpose the jth variable aj equal to 0. Okay. But look at dual feasibility. What is dual feasibility? Dual feasibility is p transpose a plus s transpose is equal to c transpose. So this p transpose a and C transpose, this gives you S transpose. So basically what you'll get is, you'll get a condition saying Sj equal to mu by Xj, which is the same as saying Xj Sj is equal to mu from this dual feasibility. Okay. So the only difference which you require to worry about is the fact that this complementary slackness is becoming a product of two numbers becoming equal to mu. Why did this happen? Because I did not solve an LP, but I solved a nonlinear program. And it's a convex nonlinear program. Okay. So what does the technique do? The technique basically what it does is it does the following. Okay. So let's say I've got a linear programming problem. Okay. It starts with a very high, very large mu. Okay. Let's say mu is infinity. If mu is infinity, in my problem, if I think of mu as being infinity, what does it actually mean? It means that I forget about my original objective function, and I'm only trying to minimize this function basically. So when mu is infinity, I'm basically solving the following problem: minimize minus summation j equal to 1 to n log of xj subject to ax equal to b. Okay. So what this does is, if my objective, let's say c is increasing in this direction, it says forget about c. Just find me a point in ax equal to b which is minimizing minus log of x. Okay. This problem is called the analytic center problem. Okay. Essentially, it gives you a problem in the center of the set, somewhere in the center of the set. Okay. So this is x star of infinity, somewhere in the center. Now what you do is you keep decreasing mu. You go from mu. So let's say this is mu old. You make the mu smaller. Okay, you decrease it. This number is basically between 0 and 1. You decrease the mu. As mu decreases, more and more x times s will get closer and closer to 0. So you're going to basically create a path. Okay. Obviously, the optimal solution here for the LP is this one, right? If C is decreasing this way, this is extra. You're going to create what is called a path of solutions, which is called the central path in interior point methods. Okay. As mu decreases, your solutions x star of mu are tracking this path. Okay. So you actually in interior point methods, you don't work in simplex. You would have started at an extreme point and you have gone along the boundary. Interior point, you do completely different. You start in the interior and you try to move to the interior of the feasible region and get to the boundary. Okay. Now the difficulty is how do you solve this for every mu? Because this problem turns out that this problem doesn't have a this problem p of mu, it doesn't have a closed form solution. Okay, like you can't solve this in closed form. Okay, so what you have to do is you have to use Newton's method. Okay, so you have to basically do a quadratic approximation of this function. That's why interior point methods work. What they will do is there's a central path. If I could solve this problem for every mu, there would be an optimal solution x star of mu, which is this central path. I don't know what the central path is. But what I'll do is I will start at this point and I will try to be very close to this central path. I will try to create new points which are very close to this path and track it till I get to the optimal solution. How do I do this? By doing a quadratic approximation to this function. So you basically you track the central path by doing a quadratic Taylor series type approximation to the function. Taylor series approximation to the function. Okay. So how does this work? So let's say your barrier function mu, let's say you're at a point x. Okay. So you're on the problem. This is your central path. Let's say you're at a point x. You try to move from x to a new point, x plus d. D is a direction. Okay. So when you go from x to x plus d, your barrier function will change. Okay. What is the barrier function? Taylor series says you can approximate it by, if d is small in magnitude, that's what Taylor series is, right? You remember Taylor series, I hope. Any function, if I take, I can write it as the sum of polynomial functions, right? X, x squared, x cubed, and so on. An infinite series. Taylor series says you approximate it by a few. Truncated Taylor series says you just take a few polynomials to approximate any function. Okay, and there are bounds on how far the Taylor series can be. But what does Taylor series say? You approximate this by the function is the original function plus take the first derivative of the function times the direction plus the second derivative, the Hessian. That's Taylor series when d is small. If d is small, this should be a good approximation. Okay. But this is easy to calculate. The barrier function. So what is the barrier function? Bu of x is just C transpose x minus summation j equal to 1 to n log of x. Okay, barrier function is very easy. The gradient is just the vector c, c1 up to cn. the gradient of log of x is 1 by x. So that's just minus 1 by x1 up to 1 by xn. That's my first derivative. That's a vector. What is the second derivative? The Hessian matrix. So diagonal matrix. If I differentiate this another time with x1, I'll get 1 by x1 squared up to 1 by xn squared. So diagonal matrix with zeros everywhere else because this is a separable function. Okay, there are no cross terms involving x1 and x2 and so on. So these things are very easy to write down. Okay, easy to express. Okay, so to find D, all I will do is I will try to choose D to minimize this bu of x plus D. Okay, how do you do that? Put derivative equal to 0. Okay, this function is nicely behaved, it's a convex function. So all you have to do is you have to put derivative equal to 0. So that's, if I differentiate this function with respect to D, I'll get del bu of x plus half. I differentiate this 2 times with respect to D, that's D squared basically. So I'll get D 2 times okay, so basically the formula for the direction, you can solve it. Okay, essentially D will be something like minus del squared bu of x, the inverse times del bu of x. Okay, this is exactly what is called Newton's method. If you've studied Newton's method for minimizing a function, you've studied this, right? Newton's method says what? You take the derivative and you scale it by the Hessian. So you apply Newton's method basically, and you solve the problem. Okay. So you don't solve the original problem, but you basically you apply, because the original problem, this finding the central path exactly is hard to do. So you do this by applying Newton's method. You keep moving this, and then you have to have some property of the way you change the mu. So there's a formula for how alpha changes. Okay, but if you change alpha in some particular way, so you keep changing mu, decreasing mu, till you converge to the optimal where x and s are equal to 0. Where the product of x and s is equal to 0. So you get very close to 0. Once you get close to 0, you know you're optimal and you can round it basically. That is interior point method broadly. Okay. Any question? I know it's quick. I know it's a lot of material. But the idea should be, what I want you to know is, you are solving a nonlinear program to solve a linear program. That nonlinear program has nice properties. You first start with solving the nonlinear program, forget the objective. It will give you a point in the center of the set. Now you try to, as you change the parameter of the nonlinear program, the mu, as mu changes, you're tracing a path. When mu goes down to 0, you get the original solution. But you can't quickly go set mu equal to 0 because you don't know this path beforehand, obviously. And you don't have a nice formula for this path. So what you do is, you take small steps. You apply Newton's method. You take a quadratic approximation of the nonlinear function, try to minimize that. Do this iteratively, and you will get to the optimal solution. This was Karmakar's method, basically. Okay. So he bypassed going to the boundary and went to the interior and solved the problem. Okay. So let me just show you one example where you can do things analytically, just to give you an illustration how this works. Okay. So just to solvable analytically. Okay. I just want to illustrate. Okay. So suppose I'm trying to minimize x1 subject to x1 plus x2 plus x3 equal to 1, but all the variables are non-negative. Okay. Just give me 5 minutes, we'll stop. Okay. I just want a few more minutes. Okay. Okay. This is a very simple optimization problem. Okay. You don't have to apply interior point to solve this. What is the optimal solution to this problem? What is optimal? X1 star should be what? They're non-negative variables. They add up to 1. So x1 star should be 0. And x2 star and x3 star have to be non-negative while they add up to 1. Any solution of this type will be optimal for this problem. Optimal value is 0. So this is a trivial problem. So if this is x1, this is x2, and this is x3, okay? Every point along this segment is optimal. Okay, this is a trivial LP. Okay, you don't require to do anything. Okay, what happens if you apply interior point method? Okay, let's think about what we will do. So you want to solve an interior point method. You want to minimize a barrier function. So x1 subject to x1 plus x2 plus x3 equal to 1. You're going to take the non-negativity and you're going to write minus mu times log of x1 minus mu times log of x2 minus mu times log of x3. I'm going to try to minimize this function. This is my barrier problem. This is my barrier function bu of x. Okay. Now in this problem, you can actually minimize this function easily. You don't have to do this quadratic approximation. Okay. Let's see how you do it. So let's try to optimize this function for any mu positive. So take derivative. So apply KKT. What will KKT say? Take derivative with respect to x1. That is 1 minus mu by x1. Okay. So actually, because x3 is given as something involving x1 and x2, so I can even take out x3. Okay, so actually I can simplify this further. So we can rewrite this. That's why I've given you only one constraint here to make it easier, to make it unconstrained. x1 minus mu log x1 minus mu log x2. So here we can just put derivatives. We don't even require KKT. Minus mu log 1 minus x1 minus x2. I'm just x3 is 1 minus x1 minus x2. I'm just plugging it back in. Okay. Subject to no constraint. So x1 and x2 lie in R2. Okay. So this problem should be easy to solve. Okay. It's a concave function. I'm sorry, it's a convex function. I'm trying to minimize. So put derivatives equal to 0. That's all you have to do. Okay. Put derivative with respect to x1 equal to 0 and put derivative with respect to x2 equal to 0. Okay. So it's a trivial problem, almost trivial problem. So derivative with respect to x1 equal to 0. Okay. So if you write down the derivative with respect to x1, you'll get 1 minus mu by x1 minus mu by 1 minus x1 minus x2. And because there's a minus 1 plus 1 equal to 0, this is derivative with respect to x1. With respect to x2 will be minus mu by x2. Okay. So I've got two conditions here. Okay. In x1 and x2. Okay. Solve. Okay. Solve. Okay. For example, if I solve this, you can check that x2 will be 1 minus x1 by 2. How? If you just take this up, you will find that x2 will be 1 minus x1 by 2. Okay, just solve this. Okay, these two equations, you can do this at your own time. Okay. Okay. So this gives you x2 is 1 minus x1 by 2. And then because you know x2, you can, once you know x2 as x1, you can write x2 in terms of x1. You can plug it back in here and solve for x1. So x1 will be 1 plus 3u. This you check out at your own time. Okay. 1 plus 9 mu squared plus 2 mu divide by 2. And then x3 will be 1 minus x1 minus x2, which is 1 minus x3 by 2. Sorry, x3 is 1 minus, should be what? 1 minus, I think, x1 by 2. That will give me 1 minus, yeah, it will be 1 minus x1 by 2. Okay. Okay. So in this problem, you can solve the problem efficiently. Exactly. Okay. So what is x1? Okay. So let's just look at x1 of u. Okay. So x1 of mu, the optimal solution for any mu, I'll just write it one more time. 1 plus 3 mu minus square root 1 plus 9 mu squared plus 2 mu divided by 2. Okay. So what is the limit? Okay. If mu goes to 0, at mu equal to 0, what do you get? 1 plus 0 minus 1 by 2, which is 0. Okay. What do you get for x1 and x2? x2 is 1 minus x1 by 2. So x2 of 0 is 1 minus x1 0 of 2. This is 0, so this half. X3 of 2 is half. So you get the optimal solution, which is 0, 1 half, basically this point. Okay, so what the interior point method does is, and you can check this at your own time, when mu is infinity, if you can check that the limit of x1 of mu as mu goes to infinity is 1 by 3. Okay, you can just check the limit of this function. You have to apply L'Hopital. I don't want to do it here. But basically, this is 1 by 3. Likewise for x2 and x3. Okay. So what happens is at mu equal to infinity, you start at the point. So this is the feasible region. You start at the point 1 by 3, 1 by 3, 1 by 3. As mu goes closer and closer to 0, you create a central path which brings you to this point, which is 0, half, and half. Okay. So one property of the interior point method is if you've got multiple optimal solutions, it will converge to the middle point basically. Okay. Unlike simplex, which will be at the extreme point. Okay. If there are multiple optimum. If there are no multiple optimum, it will go to the extreme point. Okay. Okay. Let's stop here. This was a bit quick, I know. Even ellipsoid method was a bit quick, I knew. But my goal is for these two methods, I don't think I'll be testing you definitely on details of the method. I don't expect it because I know, but you should understand for ellipsoid method the basic idea of the method, and you should understand the idea of the separation algorithm. For interior point method, you have to understand the idea of going through the interior and this barrier function, basically, this minus log x function, which is important. Okay. Details are important, but we won't have time for it in this class. Okay. Next class onwards, I'm going to start discrete optimization. It will be a different way of thinking about problems. Okay. So we'll stop here.